We will be looking at exponential functions in this video, and our three main objectives are to understand what types of functions are exponential functions, graphing exponential functions and understanding their graphs, and building exponential functions. So what is an exponential function? Well, an exponential function is one where the growth or decay, so if it's an increasing function, it's a growth function, so that means it's headed uphill. If it's a decay function, that means it's headed downhill. And basically the idea is the amount that our function grows or decay is proportional to the function's current value. The types of functions that we tend to see are things where we have a quantity that's doubling or tripling, or maybe it's growing by 3%, or maybe it's growing by something like 2.8% compounded monthly. That you should recognize that from earlier. When it's decaying, that means it's getting smaller, and the types of words we'll see is maybe it's halving, or it's 80% of its value, or maybe our function is losing 2.3% every month, something like that. Here's an example of an exponential relationship. Suppose you're given 1 cent one day. So on day 1, you're given 1 cent. So I'm going to write this as $0.01. And you're told that every day you're going to receive twice as much as the previous day for the next 30 days. So let's figure out how much we would have on day 30. Actually, we're going to figure out how much we're going to get on day 30. We're going to ignore all the other money that we got. So day 2, we're going to get twice as much here. So we're going to take 2 and multiply it by our original 0.01. Day 3, we're going to have the amount that I have here, and I'm going to multiply that by 2. So I'm going to have 2 times 2 times 0.01, which is going to equal 2 squared times 1 cent. Hopefully you can see a pattern here. On day 3, we had 2 squared. See how this number here, squared, what's the relationship between that and the 3? Well, it's 1 less. So day 4, we're going to have 2 cubed times 0.01, which is actually going to be, so this was 2 cents, this was 4 cents, this is going to be 8 cents. So it doesn't look like we're getting very far. We may not end up with very much money, but the deal with exponential growth is it grows really fast once it gets going. If I thought about day 10, this would be 2 to the 9th times that 0.01. The thing we were looking for was day 30. So we can do that now without actually doing any more work. Day 30, we would get the 1 cent, and we would multiply that by 2 to the 29. And if you plug that into your calculator, you're going to get a lot of money. That's $5,368,709.12. Exponential relationships tend to, depending on what sort of number you're multiplying by, tend to grow much faster than a lot of other types of functions. They grow much faster than linear functions. They grow much faster than quadratic functions. They grow much faster than most polynomial functions. If we're looking at a growth situation, usually it's growing very quickly. Our general type of exponential functions are things that look like this. F of x equals a times b to the x. The b is our base, and the a is our y-intercept, because if you plug in 0 here, f of 0, you're going to have a times b to the 0, and remember b to the 0, that's just 1, so we just end up with a. So our y-intercept is always 0a when we have a function of this form.
This is Desmos, an online graphing calculator that I like to use. And what we have here is a graph of an exponential function. And our exponential function form is y equals a times b to the x, just like we were looking at. And this particular one has our value of our a is 1.6 and our value of our b is 1.4. And I just want you to notice how changing a or changing b impacts the graph. As I move a and make it bigger, that moves my y-intercept here. See how it just moves my graph? As I move b, that makes my graph steeper. So it's a much steeper curve as I move my b to be larger and larger and larger. Let's see what happens when my a is negative. Right now my a is positive. If I make my a negative, then my curve, instead of being an increasing curve, is a decreasing curve. As my b changes to also be larger and larger, it's decreasing at a faster and faster rate. So it's steeper and steeper and steeper. Let's go back to a being positive. Now let's look at what happens when b is a number between 0 and 1. We never allow our b to be negative, but it can be between 0 and 1. So here my b is over 1. Once b becomes 1, then it's just a straight line, and it's no longer an exponential function. Once b is between 0 and 1 instead of greater than 1, our curve becomes a decreasing curve. The closer our b is to 0, the steeper our curve. Let's go back to an increasing curve. Also notice that as our x values become negative here, our graph gets closer and closer and closer to that x-axis. This dotted line, this dotted red line, represents a horizontal asymptote. We see the same thing when b is between 0 and 1, but instead of it approaching the x-axis when x gets very negative, it's going to approach the x-axis when x gets very positive. Let's add one more extra feature to our graph. Notice I've added a constant to our function, and when we add that constant, notice what happens. It makes our graph move up and down, and instead of having our graph approach the x-axis as the horizontal asymptote, it's going to approach this value of our c. Doesn't matter if our a is positive or negative, it's still going to approach that value of c. It also doesn't matter if our b is larger than 1 or if our b is between 0 and 1.
Let's graph an exponential function. Here we have f of x equals 2 times 3 to the x, and when we're doing our graph, we want to also locate the y-intercept and look at where we have that horizontal asymptote. So let's start with these numbers down here, because these are always easier to do than the negative values. So if we plug in 2 for our x, we're going to have 2 times 3 squared, so that's 2 times 9, that's 18. Here we would have 2 times 3 to the 1, so that's 2 times 3, which is 6. Here we would have 2 times 3 to the 0. Remember, 3 to the 0 is just 1. So that would be 2. Here I would have 2 times 3 to the negative 1. So when we have negative exponents, that means I can take that and put it in the denominator. So I'd have 2 times 1 over 3 to the 1, which is 2/3. And here I would have 2 times 1 over 3 squared. Again, that exponent is negative, so I can move the power of 3 down to the denominator. So this would be 2/9. We have all of our points listed here, and we're ready to start plotting them. Notice that we're looking for that y-intercept. Remember, that y-intercept is where our x is 0, and it's that value of our a. So that's one point that we want to make sure to have correct. So notice my values here are fairly big, so I'm going to make my scale be a scale of 2 here. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, and my x values that I'm looking at aren't that big, so I'm just going to leave these as a unit of 1. Let's plot all of our points. At x equals 1, our y value is 6. At x equals 2, our y value is 18. My y value for 3 would be way off the charts. At x equals -1, my y value is 2/3, so I'm going to have to sort of estimate. It's going to be maybe about like that. And at x equals -2, my y value is 2/9, so it'd be even closer to that x-axis. Let's go ahead and connect the dots here, making it look like a nice curve. And one thing to notice, if we look at these values here, if we choose values of x that are even more negative than -2, that's just going to make this value here smaller. It's never going to become negative though, because there's no way to get a negative number out of 2 times 3 to a number. So that value is going to get closer and closer to 0, but it's never going to reach it. The horizontal asymptote here is that x-axis. The asymptote means that our graph is getting closer and closer and closer to that line that represents the x-axis, and it approaches it, but it never actually touches it. The equation of this horizontal asymptote is y equals 0. Let's look at some other functions that we've already studied that are also exponential. Remember, we worked with compound interest, where our function looked like future value equals present value times 1 plus r divided by m to the mt. Our PV is our present value, FV is the future value, r is the annual interest rate, m is the number of times per year your interest is compounded, and t is time in years. In this particular problem, they tell us we're starting with $1,000 that's deposited into an account paying 3% compounded monthly. This $1,000, that's my present value. Our account is paying 3% compounded monthly, so my R is 0.03, and it's compounded monthly, so that M is 12. And we're looking for how much is in the account after 5 years. So my T is 5, and my goal is my future value. So if I plug everything into that formula up at the top of the screen, we're going to have 1,000 times 1 plus 0.03 divided by 12 to the 12 times 5. And this is approximately $1,162.62. We also have a new type of compound interest, and it's called continuously compounded interest. Let's look at a couple of examples of types of compounding and see what's going on here. If my compounding is compounding annually, then my m value is 1, and my future value, I can plug it back into this formula with your m equals 1, using that same scenario of $1,000 deposited at 3% for 5 years. And I can just look at what's happening here the more times per year that I compounded. So if I compound quarterly, we end up with slightly more money. If I compound monthly, end up with slightly more money. Now notice that this number here, that r divided by n, becomes smaller, but the exponent becomes larger, and it ends up, if I look at daily, there's 365 days in a year. I end up with a little bit more than if I compounded monthly. If I compound every minute, so every minute, that's 525,600 minutes, then I end up with, a fraction of a cent more than I had if I compounded daily. If I compound continuously, the formula changes to this formula. And here, E, so this means I'm compounding all the time, every instant. E is a constant like pi. So pi we know is 3.14159. E is just another constant, and it's approximately equal to 2.72. And you'll just access it on your calculator, and on most calculators it's like the second ln. Just look for the ln key, and then it's usually the second version of that. So if I wanted to figure out how much I had in the account compounded continuously, this is the amount that I have. And again, notice that it's not all that much different than daily. The last thing we're going to do is look at an applied problem. In 1968, the U.S. minimum wage was $1.60 per hour, and in 1976, the minimum wage was $2.30 per hour. Assume the minimum wage grows according to an exponential model, W of t, and t represents time in years after 1960. We're supposed to find a formula for W of t. So our goal is to find a formula, an exponential formula that looks sort of like this, a times b to the t. Now, in our statement that we're given some information here. We're given two data points. We have that red data point and we have this green information, which is a second data point. Since t is time in years since 1960, this first data point, it goes with 1968, so our t is going to be 8, and our W of t is $1.60. So there's my first data point. And our second data point was from 1976. 1976 is 16 years since 1960, and my minimum wage was $2.30. I basically have to figure out what this formula is, right? So I need to figure out what my A is and what my B is. So what I can do is I can take my two data points and plug them into my formula. So the first data point would tell me 1.60 equals A times B to the 8. And my second data point would tell me 2.30 equals A times B to the 16. Notice we have two different variables, that A and that B, and we're going to have to find both of those. So we can use that technique of substitution that we learned earlier, but it's just a different sort of context. We don't have linear functions this time. So I'm going to solve this first equation for A. If I solve this for A, I need to divide both sides by B to the 8th, and I get A equals 1.60 divided by B to the 8th. And then I'm going to take this and I'm going to substitute it in right there. So I have 2.30 is 1.60 divided by B to the 8th times B to the 16th. And notice that these have the same base, and so I can combine those into B to the 16. I can just subtract those exponents. 16 minus 8, that's going to be B to the 8th. So I have 2.30 equals 1.60 B to the 8th. Divide both sides by $1.60. Those cancel out, so now I have B to the 8th is 2.30 divided by 1.6. So I need just B, so I have to get rid of this exponent of 8. So the way I can do that is I can take the 8th root of both sides. So I can do this, 8th root, and I get B is the 8th root of 2.30 divided by 1.60. If you plug this into your calculator, you're going to have B is approximately 1.0464. And sometimes students have a hard time figuring out how to enter that into your calculator. The easy way is to use exponents. So you have 2.30 divided by 1.60. And when we have an 8th root, that's the same thing as raising something to the 1/8 power. So it might look like that, or it might look like this. If it doesn't look like it's in the exponent, you might have to put parentheses around it. So that's our value of B. To find our value of A, remember that our A was equal to 1.60 divided by B to the 8th, and so you're just going to have to store that value and then substitute it in there. And our A value is approximately 1.11. So my function, W of t, looks like about 1.11 times 1.0464 to the t. There's my function that I was looking for. In part B, it asks us, what does the model predict for the minimum wage in 1960? So remember, the minimum wage in 1960 corresponds to t equals 0. So the minimum wage in 1960 is going to be this value here. If you plugged in 0 for your t, you would get the value of your A. So our answer here would be 1.11, and this is actually per hour, $1.11 per hour. In part C, they're asking us, what is the minimum wage in 1996? So 1996, that would correspond to t equals, well, that's 36 years after 1960. And the way I found that is I took 1996 and I subtracted 1960 and I got 36 years. And so all we need to do is plug in 36 into our formula that we just built. 1.11 times 1.0464 to the 36. It's important to not round too much in our value of our b, because we've got this exponential growth, and so if you only keep like 1.04 or 1.05, that error is relatively large, and since this is exponential growth, it's going to grow exponentially. So you want to keep quite a few digits here in that value of b. Thanks for watching the video.